Evolution of stellar populations in galaxies is one of the key ingredients of our understanding of galaxy evolution in general. If we look at colors of galaxies nearby, we can immediately see that there is a bimodal distribution. There is a fairly narrow red peak, which is due to the elliptical galaxies and bulges. And there is a fairly broad blue distribution that corresponds to the disks of spirals. In more modern renderings, you can plot colors as a function of intrinsic luminosity, and you still see those same two blobs, but they're a little tilted. In the case of elliptical galaxies, that ridge line is really mass metallicity relation. The more luminous ellipticals retain more of their chemical evolution products. They're more metal rich. Metals absorb more light in the ultraviolet. Galaxies look redder. So this is largely mass metallicity sequence. For spirals, there isn't a very simple relation like that. Their colors are a combination of mixture of stellar ages, star formation rates, as well as extinction by dust. So we can produce predicted theoretical spectra of evolving galaxies in the following fashion. We have to make an assumption of what their star formation history is. This is a purely free parameter in the model, but we can make reasonable guesses. We need to know what is the initial mass function, this distribution of stars by mass when they're formed, because stars of different masses can evolve in very different ways. Then, for each stellar mass and age, we need spectra. So we need libraries of stellar spectra that can be associated with all components of the stellar population at any given age. This is actually not an easy thing to do because we can observe a lot near us. But for example, we have no spectra of very metal poor, very massive stars because those have burnt out a long time ago. And again, from theory, tested by observations of star clusters and so on, we need stellar population evolution tracks. How does distribution of stars in color magnitude space, the HR diagram, change as a function of time for a given amount of chemical enrichment and so on? If you take a quantity of gas and turn it all into stars instantaneously, a delta function star formation rate, distributed according to your initial mass function, and then follow its evolution in time. This is what's known as a simple stellar population. There is no such thing in reality, although globular clusters come close. And then you can represent net total star formation history of a galaxy as a collection of these and follow them up. One popular way of expressing star formation histories is as an exponentially declining rate, which is probably not a bad overall assumption average over many galaxies. In this case, for early type galaxies, there is a lot of star formation early on, the exponential very steep. For this galaxy, it's very shallow. For irregular galaxies, maybe essentially flat or even rising. Stellar evolution is one of the best understood segments of astrophysics. We really do know how stars work and evolve, and that's been confirmed again and again through many decades of observations. There are certainly details that still need to be ironed out, but at the level that we care about here, we really do understand that. An important thing to remember is that more massive stars evolve much faster, they're more luminous, they're also hotter, so they're energetically more important, but not for long. Thus, spectrum of an evolving galaxy will change more rapidly in the blue parts of the spectrum thanks to the short lifetimes of these massive stars, and will be changing relatively slowly in the redder parts of the spectrum where most of the light may be coming from well-evolved, slowly evolving population of red giants. There are many stellar population synthesis methods out there, and they sometimes disagree on some details, but by and large the agreement's pretty good. One popular set is called GISEL, which is a library of galaxy evolution spectra by Bruzual and Charlot. We know how stars evolve, We even have spectra of lots of different kinds of stars. And we have some idea of the initial mass function. At least we measure it locally in the Milky Way, and then we have to make assumptions whether it's the same in all galaxies at all times. We can test some of those assumptions. But then we have to assume star formation rate, which again is a completely free parameter in this exercise. This is what stellar evolution tracks look like. They're computed from stellar evolution models, and as star evolves, it moves in the color magnitude space. How and where depends very much, or almost entirely, on its mass, with minor dependence on its metallicity. So we get these stellar evolutionary tracks from theory, our understanding of stellar structure and evolution. That's pretty solid. Then we need to have their spectra. And for kinds of stars that we can observe near us, that's an easy thing to acquire. For kinds of stars that are no longer with us, say very young, metal-poor, very high mass stars, this will require some theoretical modeling extrapolation. We make an assumption about initial mass function, and again, we understand that in the local Milky Way conditions, but it could be very different in the early universe where, say, stars were made out of hydrogen and helium and hardly anything else. In fact, we believe that was the case, that initial mass function of primordial stars was very different. And then again, we have to assume star formation history. In reality, we assume some types of star formation histories, compute the consequences, compare that to the observations, and iterate until we have a model that seems to fit observations, and that's telling us what the likely star formation history of these galaxies was. So stars evolve, the blue ones keep disappearing faster, galaxies will be changing their colors, and here in color space you can follow the theoretical behavior of evolving stellar populations. You can also see where the galaxies are. And indeed, they form something of a sequence that corresponds to younger, hotter stars in late Hubble types, older, redder stars for the early Hubble types. Here is a comparison of predictions of 3 different types of stellar population synthesis models by different groups. And it shows predicted colors and mass to light ratios for model galaxies. By and large, they agree very well. The minor disagreements usually are at very young ages, and there is still some debate exactly what is the correct thing to assume. But qualitatively, at least, we understand very well how things are working. And so this is what evolving spectra of stellar populations look like. This is for a simple stellar population. Remember, this is a scoop of stars made all at once and let go. Note, these are logarithmic plots of log flux versus log wavelength, so they really hide the strong contrast. And if you stare at curves which are labeled by their age, those near the top tends to be the youngest because younger stars are more luminous. You find out that in the ultraviolet, blue part of the spectrum, the flux will plummet very quickly, whereas it will be changing in the red part of the spectrum, but much slower, which is exactly what we expect. Here is a comparison of predicted model spectra at different ages, assuming different libraries of stellar population evolution tracks and spectra. And again, you see that different models seem to be in an excellent mutual agreement, which is giving us some confidence that we actually do understand how this works. Another kind of models that are now more popular, so-called semi-analytical or hybrid models, where one can use stellar population synthesis models, associate them with galaxies that are being assembled through hierarchical structure formation, either from numerical simulation or from some statistical description thereof, and make predictions of how will the colors change and so on. There are unfortunately way too many tunable parameters in these models, And so they have some modest success, but they illustrate the complexity of all different things that have to be taken into account and a lot of assumptions that have to be made. Next time we will turn to the actual observations of galaxy evolution.